Okay, this is a quick lesson on simple machines. I'm going to take you through, I think it's 7 lessons. This intro lessons on simple machines and torque. Then we're going to do a thing on levers, followed by wheel and axle, followed by the inclined plane, the screw, pulley systems, and finally compound machines, how to put them together. The math here is going to be real simple, nothing you guys can't do at home on your own. If you watch 1 or 2 of these a day, you'll be all caught up. At the end of this, I'll post the test that I would have given you, and you guys can just do it as a take-home test. All right, so let's start off. A lever is a rigid bar. Rigid means that it cannot be bent or broken, that may rotate freely around some support, and that support is called a fulcrum. Other key terms here are that an effort force is applied to one part of the lever to move the load force at another part of the lever. One of the first questions on that take-home test will involve classes of levers and giving examples of each. So the way this came out on Notability is not the best. Basically, your key values here are effort distance, load distance, effort force, and load force. Notice that both distances, the effort and the load distance, are always measured from the force to the fulcrum. The fulcrum is this little triangular pivot point there. And then a seesaw or teeter-totter is an easy example for a first-class lever. The way that I memorize it is that you draw it with the load, fulcrum in the middle, and then the effort force on the other side. Or you can just memorize that the fulcrum goes in the middle. Scissors is another good example of a first-class lever. Moving on, the second-class lever, same idea. You've got the effort force here, the load force now in the middle, and the fulcrum on the far left. And you can memorize it fulcrum, load, effort. Or what I do is I just memorize that the load force has to go in the middle. The example I always refer to is the wheelbarrow. Your load force is right there in the middle. Your effort force is right here, and the pivot point or the fulcrum is right there. Third class lever, it's the only other combination that we haven't done yet. It's with the effort force in the middle. You got your load force on the end, effort force in the middle, fulcrum on the far end. A shovel is probably the easiest example of that, where you put all your effort in the middle of the shovel, the load is on the end of the shovel, and the pivot point would be your other hand, your hand that goes at the top of the shovel. Again, I just memorized that the effort force goes in the middle for a third class lever. The only calculation in this first lesson is torque. Torque equals force times distance, but really it's a cross product. It's the cross product of the vector of force times that distance from the fulcrum. And that cross means that the force has to be 90 degrees to that lever arm, which in this course, in all cases, it's going to be. We're assuming that those forces are all 90 degrees to the lever arm, even though we've got these drawn on a slight angle. We assume that they're always going to be 90 degrees to the lever arm. Now, we do have to know what the consequences would be if the force is not at 90 degrees. We get the greatest torque when when the force and the distance are at 90 degrees to one another. And you get no torque, or a minimum torque, when the force is right in line with the distance. So no angle or 180 degree angle between them. So if they're in the same line, you get torque equals 0. And if they're 90 degrees to each other, your torque is equal to a maximum. So all you're really going to be asked to do is calculate torque with this. So let me just show you a few right here. I'm going to start at the top right just because I see some space there. Torque equals force times distance. That's 2.5 newtons times 25 centimeters. It's a little ugly. I'm trying to write with a stylus here. So I just type in 2.5 times 25 and it's 62.5. So I'm just going to write that right here, 62.5. Now you probably would wonder about the units. If we're going newtons times centimeters, then it's just Newton centimeters. I suppose Newton meters would be the SI unit for it, but for this chapter, it doesn't really matter. You just put together the two units it gives you. If you're going newtons times centimeters, it's Newton centimeters. Down here, bottom right, torque is going to be force times distance, 250 pounds times 1.3 feet. And I'll just type that one in. 250 times 1.3 gives me 325, 325. And if you guys are in auto shop and that, you might measure things like torque in foot-pounds. So I'm going to write that. It doesn't matter the order. Pound-feet would be the same thing. I just know that's a little bit more common to hear in the shops. Looks like I got space to do one more here in the bottom left, and I'm not going to do that first one because there's no room to do it. So this one's going to be torque equals force times distance again. So that's going to be 5.5 newtons times 1.5 meters. And finally, this one here will be 5.5 times 8.25. This is the only one that's in the standard international unit. But that's okay. For this chapter, it doesn't matter. Newton centimeters on the first one, foot pounds on the second one, Newton meters on the last one. Your units don't matter, just put them together. This last one here, it just says that you've got a door. You're going to push with 50 newtons on the right, the pivot point's here, and you've got 1 meter distance from the fulcrum. Extremely easy to calculate this. Torque equals force times distance. That is 50 newtons times 1 meter, which is 50 Newton meters. So that's how you calculate torque. Now I know in this particular lesson there's no examples on calculating the other quantities. So if I go back up to that slide with the formula, if you guys need a crutch like this, torque, force, distance, that way if you want to solve for distance, you go torque divided by force. If you want to solve for force, you go torque divided by distance. It's that easy, much easier than the stuff that we were doing right before the break, which is why I'm choosing for you guys to do this at home. So that's lesson number 1 of, I think, 7. And yeah, I may post some practice to go with this, but I think that this stuff is so simple that I'll just, the only thing I'm going to assess you on is that take-home test at the end. So you guys have watched through this now. You can go back and take notes if you want to. It's up to you. Whenever you're comfortable enough with the material, then I encourage you to go do that take-home test. And I'll figure out how exactly I want that to be submitted to me after. All right, that's it for now.